So welcome to part 2 of our discussion about orthonormal sets and the Gram-Schmidt process. Now we just said we defined what an orthonormal basis is, and what other further properties can we deduce from that? Well, there's some nice things that we can deduce. So if we have an orthonormal basis for a vector space, then for any vector space V, you can write it as the inner product of V E1 times E1 plus V inner product with E2 times E2 all the way up to V the inner product of V and En times the vector En. So this is very nice, but you have a way of writing V as the linear in terms of the basis elements using the inner product. And the other thing that we have is that the norm of V squared is simply the absolute value of each of these inner products squared, and we take the sum of all of those guys. So we take the inner product of V with respect to the basis element, we take their absolute value, and then we square that value. Now 2 actually just follows from 1. 2 follows from 1 and the previous result. Okay, so and why is that? Because E1 through En are linear or orthonormal, we know that the norm is just simply the coefficients that show up when you write the V in terms of the linear combination. So what about the first part? Okay, well, we know that since E1 through En is a basis, V can be written as some sort of linear combination of these vectors E1 through En for some A1 through AN. Okay, and now our goal is to say that we can actually compute what these guys are using inner products. Okay, so if we take V and we take the inner product with E1, that's the same thing as doing A1 times E1 up to AN times EN and the inner product with EI. Okay, now you're using the properties of inner products, right? So this can be written, and I'm doing kind of a whole bunch of steps simultaneously. So this is equal to A1, the constant A1 times the inner product of E1 and EI. And then we have in the I spot AI, the inner product of EI with itself. And then we have AN, EN, and the inner product of EN and EI. Okay, now so we have to think about what all vanishes here. Okay, so what we know vanishes is because the EI is the orthonormal basis has the property that it's orthonormal, each of the vectors are orthogonal to each other if they're distinct. So anything that like E1, EI, E2, EI, they all go to 0. So you're left over with AI times the inner product of EI, EI, right? Because since EJ, EI is equal to 0. That's one of the properties of an orthonormal basis. And then, what's the inner product of EI with itself? Well, that's just going to be 1 because the norm of EI is 1. So this is equal to AI. Okay, so that actually finishes the proof because it's just saying that the AI, the coefficient AI is just equal to the inner product of V and EI. Okay. So a very nice consequence is that it's very easy to express V in terms of the basis if you know it's orthonormal. Okay, so just to kind of reiterate why this is nice. In general, if you have a basis, you have V, and there are coefficients that allow you to do this. But when you have an orthonormal basis, you actually have a formula to compute what all of these EIs are. They come from the inner product. So that's one of the huge advantage of having an orthonormal basis. It's very easy to express any vector in terms of the basis. Okay, so hopefully this kind of convinces you that orthonormal bases are important, okay, and I would say that this is kind of probably one of the most important properties of an orthonormal basis, the first one. And so the question is, can you find them? And the nice thing is you can find an orthonormal basis for any inner product space using the Gram-Schmidt process. Okay, so as I state the theorem here, I just want to remind you that we actually did this, but we only did this for V is equal to Rn with the dot product. Okay, so we actually just did a very specific example. Our example was a very special class of vector spaces, and we were only using one inner product. But it turns out there's nothing special about the V here, and there's nothing special about the inner product that we use. We can actually adapt that proof to prove for any vectors, for any inner product space. Okay, and now I'll put the statement up here, and I do want to make a couple comments about it. Okay, so the comment is, suppose that you have a collection of vectors and it's a linearly independent list of vectors. Okay, so there's no condition on these vectors except that they're linearly independent, and we're working in inner product space. And what you're going to do is let E1 be the first vector divided by the norm of the vector, and for j going from 2 to m, we're going to let Ej be equal to Vj minus this vector right here. So this vector is formed by taking the vectors E1 through Ej minus 1, which we would have found previously. And we're computing all these inner products, and we're dividing it by the length of that vector that we found. Okay. Then, what's our conclusion? Then E1 up to Em is orthonormal, and the span of these vectors is equal to the span of V1 up to Vj for j going from 1 to m. So in essence, what you're doing is kind of like an iterative definition. You first define E1. Once you have E1, you can make E2. Once you have E1 and E2, you can make E3. And at each stage, what you're doing is you're changing the linearly independent elements V1, V2, and so on up to Vj. You're turning it into another list of linearly independent elements, E1 to Ej, such that the new list, not only is it linearly independent, it's also orthonormal. So you're kind of changing changing one basis into another basis. So you're using the VI's to make the EI's, which are going to be an orthonormal. Okay, and this is a little bit different than the process that you would see in Math 1B, since what we're going to prove is that each step we're making a vector, we're making the vectors, it shouldn't be, we are making vectors of norm 1 at each stage, at each step, but we didn't do this in 1B3. In 1B03, we first found orthogonal vectors. We didn't really care about making the vectors all the correct norm as we were going along. We were just worrying about the other part of the orthonormal definition, is that each of these pairs are orthogonal. And then at the end, we might have made it into an orthonormal set. So keep that in mind when you think back and you look back at your Math 1B notes. Okay? So we'll pause here. When we come back, we're going to prove this particular statement.